Hello, everyone. My name is Marie Correcla, and welcome to today's AIRAH Streamline session. I hope everyone's having a good week so far. Today's webinar is supported by Litmas, and today's talk will be on interaction of people, buildings, pathogens, and our external environment. It would look at how we view our indoor air quality and how the way we view indoor air quality has effectively changed throughout the COVID pandemic, and we'll have a look at the reasons as to why that has changed. Just some quick housekeeping before we do get the session underway. If you've got any questions throughout the presentation, please type them into the Q&A box that's located just at the bottom of your screen, and we'll do our best as always to try and get through as many questions as possible in the time permitting. So today's presenter is Dr. Claire Bird, and Claire's career spans research and commercial engagement within the chemical and microbiological environment. Claire was heavily involved in the development and review of the second version of the NABERS indoor environment rating tool. Claire's also an active member of AIRAH's Indoor Air Quality Special Technical Group. And Claire ultimately has been heavily involved in helping to drive the indoor air quality industry for many years in Australia. So Claire, I think it's time I hand things over to you, and you can get the session underway for us. Thanks, Claire.
Okay, hi everybody, yeah, happy Thursday. It's nearly the end of the week, so hopefully this will give you some food for thought for the weekend. What I'd like to talk about today is how our perception of indoor air quality has changed as a result of the COVID pandemic, and how we've responded to that in terms of how we operate our buildings, and in particular our HVAC systems, and what that leaves us with when we actually have to make decisions about the best control measures to be able to achieve a better environment indoors and outdoors. So why we're here and why today? Well, that's because our view of air quality has changed so much as a response to the pandemic. So what I hope to get out of today is to examine how the interaction between buildings, people and the environment has changed since COVID. Also, a part of that we'll look at considering what may be missing when we're thinking about controlling infection transmission. And I want to consider the impact of the sort of air quality and transmission mitigation strategies on the broader environment and its impact on our energy burden and global warming burden as well, by putting in place preventative measures for infection control and improving our indoor air quality. But it's really important when you do any of these sorts of talks that you propose a way forward, and that's something I'll do at the end of the talk. So certainly public perception has changed. When I think about it as a consultant, I used to get calls from people, and their number one concern will be odour. The second concern will be mould. The third one would probably be something that smelt, that was often a VOC or a sewage-related issue, and they'd be worried about having too many children in the classroom and how carbon dioxide might be affecting performance in their workplace or learning centre. The other thing people were concerned about was external pollution, particularly if we look at developing countries where external air quality is very, very poor. We intrinsically live outdoor air in our indoor environments. We can't survive without it. So, even things like wastewater treatment plants and compost operations can lead to odour problems and other microbial concerns. So that's really where we were thinking. But then came the pandemic, and we had a lot of exposure through both social media and the media generally, and our focus changed to really being pathogen-centric. And we started to think about what part the carbon dioxide might play in helping us control our air quality. People were still concerned about mould, probably more so than ever, VOCs, and we've just seen a huge uptick in indoor air quality services demand across the industry. Scientists are also looking differently at air quality, and we're looking at it these days through a lens of transmission. So pre-pandemic, the biggest concern for scientists were probably volatile and semi-volatile organic compounds in terms of health risks. Certainly carbon dioxide was still an issue in terms of performance and health, ingress of external pollutants, and dampness. Dampness in buildings is what makes people sick, and we'll talk about that a bit later when we touch on a little bit about mould, because that's what I do these days. Is I run the mould analytical laboratory, and we look after contaminants from buildings primarily that are microbial in nature. The other thing which we were concerned about was emissions from our air conditioning system from mould, but also we were concerned about, had some concern about Legionella and controlling it and monitoring it. And we were concerned about Legionella in dead legs in plumbing systems and in faucets. And yes, we were worried about great greenhouse gas emissions and climate change because this affects so many different things. But during the pandemic, when we first got the pandemic, everybody was focused on near field transmission, droplet nuclei. Everybody was washing their hands like crazy. Everybody was aware of social distancing. But very early on in the piece, we became aware of the fact that COVID was probably airborne. And a lot of the scientific effort was put in place to try and get this taken on board. And where we find ourselves now is that indoor air quality research and interest is sharing the space with infection control. Whereas before, infection control was much more the remit of people looking after clean rooms or hospitals or clean environments. We've now got whole monitoring networks of carbon dioxide sensors deployed to make sure we've got adequate ventilation. And we're seeing new threats emerging. We're seeing outbreaks of Legionnaire's disease from cooling towers because buildings are sat empty. We were seeing Legionella coming from these sort of dead areas in plumbing systems. So we've seen a real shift. And actually, and of course, the other thing we've experienced in Australia was these awful floods. So people are really, really concerned about mould and about other microbial contaminants in buildings. We still, as scientists, are concerned about semi-volatile organic compounds. And we'll talk a bit about those in the next focus was always on building emissions, whether that be greenhouse gas emissions to the external environment, these things that were coming off our HVAC systems like mould and Legionella, volatile and organic compounds, outdoor pollutants coming into the building. But our main focus was on thinking about reducing the emissions from that may affect our health. We were looking at controlling emission levels from VOCs from products. We were looking at preventing ingress of these external contaminants, whereas now we've become much more exposure prevention focused. It's much more about reducing what people are exposed to, assuming it's already in the air. And I think that's come through the fact that we've now got we've had much tighter time restrictions around the investigation time. We've had to come up with strategies to control what we face. So the simple answer is dilution being the solution to pollution. So I guess that the other thing that's come post-pandemic is that people have now got this feeling, well, if we're diluting pathogens, we can just deal with everything else, indoor air quality related at the same time. So I guess the other thing we saw with the election is the public interest in climate change and the importance of controlling it. The other big factor that hit us just prior to the pandemic, of course, was the awful bushfires that we had. So post-pandemic, we've still got a lot of these concerns, but we seem to have shifted to a concern about protecting ourselves rather than preventing emissions, and that will be a focus of today's talk. So we saw hugely variable responses by the government to accepting airborne transmission and looking at how we improve our ventilation. And in November 2021, the AHPPC did produce advice on ventilation air purification, but it's only a few months ago, and we've been living with this for nearly 3 years. And if you look at the Safe Work website and you look under their COVID section, they tell us it's reviewing it, but at the moment, it's still telling us to keep away from people and wash our hands. Whereas if you look at the Victorian government, which is kind of roared ahead with this, they've got in place their ventilation principles and strategies to reduce airborne transmission. They've got rebates in place for small businesses wanting to increase ventilation. They've got a stimulus package, and they've recently produced their ventilation policy as well. Whereas New South Wales are now being encouraged by scientists in Australia to follow Victoria's lead, and they just haven't kept pace. So it's very variable across the country. Now, foreseeing that this was going to be a problem, there are now groups of experts across the world who have got together and joined forces. And in Australia, Our leading drivers in this area is a group called AusSage. This is something that our very own Lydia Morawska and Kate Cole, who's president of the AIRAH, has been very involved in driving. But there's a huge number of very, very qualified scientists and people that are involved at different levels with building safety, who've got together in Australia to try to drive this change and acceptance of airborne transmission. I'm part of a group in Canada, which is the equivalent group called the Canadian Aerosol Transmission Coalition, who are doing the same thing there. And I'm Executive Secretary of the Integrated Biosciences and Built Environment Consortium, which I'll tell you a bit about in a moment. But we have been put together a global group to look at how we can get on top of airborne transmission and manage it through these strategies that we're all familiar with at AIRAH. The AMCA pulled together, Ben Hawkins pulled together a wonderful group of specialists from building performance assessment through to portfolio management and everybody in between to start to look at how we could, again, get this airborne transmission taken seriously. And of course, AIRAH is leading the way in providing some great resources and providing webinars like today to really highlight that change. So I'm just going to tell you a little bit about IBEC because we are working with AIRAH on part of our programme. So the Integrated Biosciences and Built Environment Consortium, we are IBEC, is a volunteer not-for-profit organisation that's headed out of the US. It was instigated by Dr. Janie Moreau, who was a former executive director under the Obama administration for science and technology. Ken Martinez, who was former head of biosafety for the CDC, and Tony and Ted Cowan, who are brothers, one of whom has been at the forefront of the emergency response and the other who is involved in producing very high-end medical equipment. They started IBEC with the aim of making science easily accessible to the public. We've got a team of over 30 scientific advisors, several now from Australia, including Professor Morawska and Brett Cole from Biosafety, and we've even got an outstanding organisational psychologist on board from Australia too. And we're currently advising the White House on airborne transmission. And as part of that, we've developed a platform, or will be developing a platform to find out what gaps we have in consensus standards globally for indoor air quality. We provide a series of clean summits that have covered topics such as vulnerable workers around the pandemic. And we run a series of lessons learned webinars that are there to get the public comfortable returning to everyday activities. As part of our work, we developed the Commit to Care programme with the American Industrial Hygiene Association based on a Centres for Disease Control funded grant that's provided a terrific resource package of research documents and micro training modules for both individuals and organisations to be able to conduct a risk assessment of how they can best prevent transmission of disease in their organisations. And it's a great tool. Organisations can show that they're doing this and that they're doing the right thing and they have undertaken a proper risk assessment of their particular operation. And it's through that package that we've teamed up with AIRAH. So AIRAH is one of our amazing collaborators in promoting the Commit to Care package. Other people have been included in Australia at the Australian Institute of Occupational Hygiene and the Indoor Air Quality Association Australia. We've got the International Society of Indoor Air Quality. We've got some very significant US organisations such as the US National Safety Council behind it, as well as organisations all the way out in South Africa, where we've got the South African Institute of Occupational Hygiene supporting this. This has been an absolutely fantastic programme, so we're delighted to have AIRAH on board and be working together on this. So in America, as a result of all this, the government's catching up, which is great. So certainly in Australia, we had to get 200 scientists together, which was led by Professor Morawska, back in July 2020 to get them to take airborne transmission seriously. And what we were seeing was that the CDC and the World Health Organization were just clinging on to transmission from surfaces like death. And they finally have rescinded and admitted that we had aerosol transmission really relatively recently. So what is indoor air quality and what does it mean outside of disease? Well, any disease or contaminant becomes a pollutant when it's at a high enough concentration to make us sick. So it can be an individual compound, or it could be a physical, microbiological or chemical component, or it could even be a combination of those that leads to adverse health effects. So just a very quick scout through a list here of some of the gaseous contaminants that we're familiar with in the indoor environment. The semi-volatile compounds, a lot of them come from things like flame retardants. They're very much a work in progress and known to have significant health effects. Particulate pollutants are very wide-ranging in the indoor environment, from asbestos and respirable silica due to incoming diesel particulate from traffic fumes, fungal and bacterial spores and fragments, and of course viruses are particles. And in fact, viruses are quite unique, or kind of unique, in that they're what I've phrased or coined a multi-phase particle. It's a solid particle of virus entrained in a liquid particle of mucus. And when you've got these sort of multi-phase particulates, they can actually behave quite differently to things like an asbestos particle, which is effectively a physical particle. So we'll have a little look at how that may impact the control measures we might make in terms of filtration and ventilation in the environment for these types of particles. The other indoor contaminant which we don't hear as much of in Australia is radon. So what we have in the environment at any time is a balance of what's come into the environment from the sources. And here's just a list of some of them, things like gases from paint and adhesives. It can be particles from microbial growth or exhalation of these multi-phase particles, and particle and gases that are coming from outdoor air through fresh air intakes. And once those particles get in the environment, they're constantly being settling onto surfaces and constantly being resuspended. And at any point in time, what we're exposed to in the air is really a balance between what's being released and what's being taken away. So some gases absorb onto the surface, as we react with the other gases. Some get taken out of the building with return air and extraction, and other particles are just lost to outdoors just through general air exchange through the building envelope. So at any point in time, what we're exposed to in any space is a balance between what's come in and what's gone out. And that balance point is constantly changing. And what we're exposed to is whatever is in there at that point in time. So if we're unlucky and there's enough virus released into the environment that hasn't been diluted or removed, then we can catch an infection, or if it's a chemical contaminant, we can get sick. So how do we prevent transmission? What are the things that we consider? So IBEC has actually devised, with the AIRAH, devised the 4 Ds. So that is density, distance, duration, and dilution. And there's some things that the person has control over. You can decide how far away you are from someone and how much time you spend in a space. Obviously, the closer you are to somebody and the longer you spend there, the more likely you are to get an infection. You also can play a part in diluting the virus, because if you've got the virus and you wear a mask, then you're not going to make the concentration in the air as high. If you're in a room and you've got virus in the air and you wear a P2 respirator, you've got less likelihood of being infected. And it's really worth pointing out that there's some reconsideration being made of masks at the moment, because the BA4 and BA5 Omicron variants are highly transmissible. We're now saying that P2 is really potentially the only suitable mask for preventing infection spread, which is a shift from surgical masks with the earlier variants. In terms of what we can do with our buildings to change infection spread, we can reduce the density of people in the space, and we could dilute the pathogens through ventilation or filtration. Also, another thing we need to sometimes think about is direction of airflow. So for instance, in transport vessels, having lateral airflow allows you to very easily move a viral pathogen from one person to another, where vertical air movements do that a lot less. What's very notable is that under the current transmission models, and this includes a recent Versant model, if we start to look at what you can do to reduce your risk of infectivity, you actually find that the transmissibility of that virus becomes an overriding factor. And by the time that virus is in the air and you're having to dilute it, it's already there. So preventing it getting into the air is what the shift in paradigm I'm trying to make today is. So I'm just going to ask a question of, let's look at this model again, but actually look at it from the perspective of somebody being infected. If we've got a high density of people in a space, like for instance in a classroom or a place of worship or a transport vessel, we've now got a higher chance that somebody is going to be infected in that space and infect other people. From the distance point of view, the distance that infected person is from everybody else will determine how likely they are to infect someone. From a duration point of view, the longer they're in that space infected, the higher the load's going to be in that space. And there may not be a lot we can do about those things because we don't know who's infected. But dilution is interesting because the only way that we can dilute that source of infection is through stopping it within the breathing zone of that person before it gets into the general environment. So there is a shift here that we're not necessarily thinking about. And as somebody who spent a lot of time also working in the external air quality environment, I'm very familiar with some of these different types of ways we look at emissions. And we have area sources where there's emissions coming from all different places simultaneously, like bushfires, agricultural, fuel stations, because there's lots of fuel stations around the place. They're all areas. Mobile source emissions include trains, aircraft, and even lawnmowers. But we also have point source emissions where we know that we've got one particular place that's releasing something. So it could be a sewage plant or a refinery. And an area emission source becomes a point source where it can be traced back to a single point of release or generation of the pollutant. If there are many identical point sources in a given area, it then becomes considered an area source. And this idea of having a point source where we can identify that contaminant back to one place versus an area source actually plays into how useful ventilation is in what we're doing. We've got some examples of point source emissions. They're obviously an infected person coughing, other biological aerosols in buildings come from toilets, food waste. Even if you've got a lot of plants and soil around the place, they can actually create a localised source of particles. In terms of construction activities, things like release of asbestos and respirable silica and lead-based paint normally happen around a place where the work's actually taking place. So they're also a point source. And then you've got printers, you can have cookers in kitchens, and you have naked flames in fires or even gas fires. And all of those are point sources of pollution. The other thing is if you've got a very localised damp spot, a building material, that can create a growth of mould in a very localised location. Another example is if you've got a contaminated duct just in front of a supplier register, that's a local point source of emissions. Area sources are quite different, so things like carpets and timber and resilient floor coverings, furnishings are spread throughout the building and they're constantly potentially releasing contaminants, so that's an area source. Contaminants coming in from outdoors from a big open window quickly mix in that environment and become an area source, and that's the same for anything coming in our fresh air intakes. If you've got a lot of people in a room, they're all exhaling carbon dioxide and water vapour, that's an area source. So we're looking at the moment in monitoring an area source to control a point source. We're monitoring carbon dioxide, which comes from everybody in the room, to control concentrations of something that's coming from perhaps one person in that room. So that's interesting. If you've got damp building materials from condensation, you might have much wider growth of mould over larger areas, or if it's further back in your air conditioning system and it's being passed through your supplier, then that obviously creates an area source. If you've got a lot of people infected in a space like something like a cinema or classroom, then you've got an area source of infection as well. And the other thing that we often forget when we're thinking about things like ventilation is how the air movement and dead spots might affect the concentrations in that room. You might have an area of a source of contaminants, but they might end up accumulating in one place. Or you might have a very localised source that very quickly gets dispersed if you've got very good mixing. The other type of area source are secondary pollutants. And these are things that are created when gases in the indoor environment react with other gases or are affected by things like ultraviolet light. We'll look at that later. Or some people use ozone for air purification. And if they react with certain terpene-based cleaning products, they can produce secondary particles and aldehydes, which are potentially carcinogenic. And obviously HVAC systems can take contamination from one place and move it somewhere completely different. So whilst there wasn't an immediate source of contamination in an area that's at the end of a supply, it could be picking stuff up from where the return was servicing that area. And that's a secondary contaminant. It's not caused within a space, it's generated elsewhere. So this is where it gets interesting. When we want to manage area emission indoors, like carbon dioxide or VOCs, ventilation is perfect because we're going to reduce the concentration of those contaminants. Okay, filtration is great if you want to move large quantities of particulate matter. So you're going to be dealing with large quantities of air through your filtration, and that may be in your HVAC system, or it may be on a mobile filtration or air purification device. And there's a lot of standalone air purification technologies out there, which we'll have a look at. But when we deal with point source emissions, normally I was speaking to Patrick Chambers about this the other day, and he and I hope to present a follow-up session to this on a topic which you guys would find the most useful on the back of this discussion later in the year, which Marie can tell you a bit about. When we think about point sources, we don't normally deal with them using ventilation. We deal with them with extraction. We have extractors in our toilets. We have local extraction if we're doing any sort of manufacturing with chemicals. And even if we're doing a strip out during asbestos removal or mould removal, we put up containment around that space and we contain that contamination to that point. And then we actually put together a whole range of flash equipment to set up a pressure differential so that all those contaminants are drawn out to the outside of the building and don't go and contaminate the occupied space. We have local filtration and air purification where we have these sources. And again, with the industrial applications, you're often even having chemical air scrubbing specifically designed for those local generations. And yet we haven't thought at this point about infection as being a point source of contamination. And of course, as we've developed our buildings, we've made our buildings increasingly airtight. So the type of ventilation that we're looking at may be increasingly mechanical, but we still have an awful lot of buildings in Australia. I think 80% of schools are still naturally ventilated. So we've still got to look at supplemental technologies to actually keep air quality satisfactory in those spaces. So, natural ventilation is difficult to control. On its own, it needs assessing this dilution may not have been enough to reduce transmissibility or bring those airborne contaminants down to a safe level. The occupant density and the occupant activity in that space may determine how adequate that ventilation is. You've got people singing or you've got people working out in a gymnasium, you've got a much higher rate of expiration of viruses and any respiratory-borne contaminants. And as I said earlier, one thing we're finding is that when we model air exchange rates, it's not always adequate to control infection spread in densely occupied spaces. So that's where we may need supplemental air purification technologies to mitigate infection risks. The other thing with opening windows is it can lead to noise complaints. It can also mean that there's a draft coming in and people become uncomfortable. So that then starts to affect thermal performance of the building. We need to think as well when we're increasing fresh air intake about what we're bringing in from outdoors. We don't want our fresh air intake chugging away if it's going to bring in more contaminants from outdoors than we've got in the environment. So if we're very close to a road and we're in an urban area, there's part of the contaminants to be concerned about. If we're near an industrial site, then obviously there's other contaminants that we need to think about filtering out of our air that's coming into that building. Obviously, bushfire is a key one. If we're going to be changing our systems to move towards intake of more external air, how are we going to manage that when we know that we've got a very serious health risk coming from outside? We still need to have the flexibility for our systems to be able to handle these sorts of changes, especially in a time of climate change. And obviously, there's microbial contaminants and odours we want to control from things like wastewater treatment plants and compost works. Odour itself is actually quite an interesting beast. Even though the gases that create an unpleasant smell may not be present at a high enough concentration to make us sick, they can actually make us quite sick due to anxiety. Anxiety actually elicits very significant biochemical changes in our bodies that can lead to mental health illness. And it's not in our heads, it is actually a physiological response. The other thing we need to think about is how much humidity and moisture is in that incoming air, because that's going to really impact how efficiently our systems will be able to work, and that's what we'll look at. Some of the financial considerations we're changing the way that we handle our air is going to be operational costs. So we're expecting an increase in energy use and therefore global warming impact. And there's also an anticipated increase potentially in frequency of how often we need to replace our filters if we're bringing more external air in. There's also an opportunity cost here because amenity suffers if we're not handling our air and managing it so that it's still as thermally comfortable. If we're starting to change the velocity of the air coming from the supply air grills, that can also change the value, perceived value of those asset portfolios. The other big factor that's happening is that humans are deciding to do things differently, and therein lies a problem when we're promoting ventilation without explaining to people what that means and what the risks are, because it can lead to unintentional changes in airflow patterns in buildings if we change air ventilation, but we haven't actually understood how the air is moving through that building. And certainly in Amoy Gardens, when we had the very first outbreak of SARS before SARS-CoV-2, we know that emissions from buildings that were venting, particularly from toilets, out of apartments, were being picked up on air currents and carried a kilometre away, where they were making people sick in adjacent buildings. And certainly one project that I was involved with in Queensland was actually an odour project. We were tracking an odour issue with tobacco smoke. And what we found was that if you've got a hallway that's positively pressurised and then you've got an apartment with a patio door closed, that apartment is always under negative pressure in relation to the hallway. So air doesn't move from the apartment out into the corridor. But of course, as soon as somebody opens that door, then air's now moving from that apartment more freely into the corridor. And because the corridor is under positive pressure, that's then pushing the odour into the apartment next door. And this is potentially why we have seen the big problems that we saw in spread through multi-storey buildings when we had a lot of people under lockdown. So just opening windows and ventilating and giving people this simple message, open your windows and hey, everybody's, going to be healthier, isn't necessarily true. And it's our responsibility as AIRAH, I think, to manage that. And the other thing is we know from the research that increased humidity makes people think their indoor air quality is worse even when it isn't. So what actually changes if we have more humidity in our buildings because we're trying to handle more air and the air's humid? Well, we certainly do see increases in levels of organic contaminants, some of which are very harmful. So it seems to be above 50% humidity, you're really starting to see increases in release of formaldehyde in buildings. And again, you're seeing increases in levels of volatile organic compounds. So if we change the humidity in our buildings, even by, even within a range that we're normally comfortable, we could be changing the amount of these contaminants that we have in the air at any point in time. The other thing that happens when the humidity increases is you change the microbial profile of the building. So this little table here, we don't have to look at it in any depth, but what I will explain to you is that the primary colonisers are the moulds that arrive first when a building starts to get slightly damp. And mould will start to grow when humidity at the surface of a material reaches 80%. The number AW is what's called the water activity of the mould. So a mould with a water activity level of 0.8 will grow when the surface reaches 80% humidity. And as that humidity goes up, those surfaces are becoming increasingly likely to become more damp or more tend to having a tendency towards having higher humidity on them. And the more humid that environment becomes, the more likely you are to shift that microbial profile to one actually more harmful. And what we have to remember is that the ambient humidity might be, say, 75%, but if the surface is cooler, then the humidity on that surface will be higher, and that will encourage mould growth. And when mould changes in the building, it's not the only thing that changes. And one of the key misconceptions in indoor air quality is that mould is the only thing that makes people sick in damp buildings. That certainly isn't known to be true. In fact, bacteria are playing a key role. And once the building gets damp, you get increases in dust mites, cockroaches, and even rodents that lead to quite substantial shifts in the health status of that building. And if you've got any sort of thermal bridging, which is what you can see in the red spot here, then that will become increasingly likely to grow mould if your humidity goes up. And maybe the take-home message from this slide is you don't need condensation for mould to grow. That surface just needs to start to reach that 80% humidity. And while we're on microorganisms, we're back to our friends pathogens. And we know that SARS-CoV is a very recent article really come out in the last month. There's been some work conducted where we've now shown that with humidity levels above 50%, we're getting much longer survival of SARS-CoV-2. And so if we don't manage our humidity levels in the building, increasing the effectivity of these organisms because they survive longer in the air, so there's more chance that if you become exposed to them, they will make you sick. In terms of semi-volatile organic compounds, they're phase shifters. They're quite interesting. They're unique in that they move between the solid and gas phase quite frequently. And that change seems to be driven by temperature rather than by humidity, for what we could tell at this stage. So there's still a lot of research going on in this area. But again, we need to keep an eye on any changes we make in that internal environment to make sure our ventilation is adequate to remove any increased risk. Okay, so how does increasing ventilation impact energy use in buildings? Well, filters can become more blocked because you're bringing in more outdoor contaminants and particulates, and you're recycling more air through the system. If you increase the volume of fresh air being handled, then you're going to be increasing your pump use. And if you're increasing the proportion of fresh air compared to recirculated air, you're now having to heat or cool more air or take moisture out of more air. And that's actually going to increase your energy use. And the interplay between moisture and energy is important, because when we cool air, we remove the moisture, usually by refrigeration. That requires energy. And when external temperatures are warmer than our inside, we have to cool air. When humidity is high, we have to cool air. When larger volumes of air are handled, we're cooling more air. So these are all places where we start to create an energy and a global warming burden on our activities. And where moisture ends up in the building is important. We've seen the impact that humidity changes can make to air quality and thermal comfort. But also, if we've got a lot more liquid water in the building, say in cooling towers, then that may increase our tendency to release things like Legionella. So it's important that we think about how our systems are working. And if our systems aren't working effectively and we're changing the temperature, for instance, on our cooling coils, that may change the microbiome, that is the types of microorganisms that grow on them. And they may then lead to a different release of airborne microorganisms into the environment. So when we increase energy, we know that we're having a significant impact on global warming burden because we still use fossil fuels in a majority of cases for our heating and cooling. Fossil fuels remain a key contributor to greenhouse gases. And because we've already got to the level where greenhouse gases are causing harm, any additional greenhouse gas leads to further change. And therefore, all greenhouse gases are pollutants because they're changing the environment. They're changing our terrestrial communities, they're leading to flooding, bushfires, changes in soil moisture, which are affecting our agriculture industry. We know that we're seeing changes in aquatic communities, and we're seeing changes in things like migratory patterns in birds and bats and insects. And we've seen what's happened with COVID, but insects carry a significant number of diseases. So the changes in their niches is impacting health as well. We're seeing increased disease spread through flooding in particular, and general environmental changes. And also when we have catastrophic events, that does lead to significant mental health impairments in people that have post-trauma. We see economic impacts, of course, to our farming, travel and energy markets. And obviously we're still building and infrastructure damage, which we're very familiar with. So we've got to be very mindful that if we're going to make a decision to increase our energy burden, it's actually going to help us in the long run. Because Australia currently uses about 13% of its energy for residential and commercial buildings, and then 26% is actually getting that electricity to people. So, you know, there's actually a big burden in electricity when we use it. And interestingly, we put more energy into heating our buildings and cooling them, and that becomes even more noticeable when we look between different jurisdictions. We can see that in the winter, which is the grey bars, that tends to use a lot more energy than the brown bars, which is in the autumn, and the blue bars in the summer where we're cooling. It's also interesting to see that even though Tasmania and ACT are cold in the winter, as Victoria is, there's a very significant difference in the amount of energy use per household in each of those states. So other factors that we'd like to quickly look at to finish off on ventilation is, what does ventilation also do? We're ventilating the building for pathogens. We're also diluting air, other airborne contaminants. We're diluting indoor odours, and we're diluting carbon dioxide, which makes the environment a lot more comfortable to live in. Carbon dioxide emissions do not equate linearly, however, to transmission of virus. So partly because we're looking at carbon dioxide, which is an area source coming from a point source, but just partly because viruses are particular. So we said that we're looking at supplementing with high efficiency particulate air filtration with HEPA, which can be integrated into HVAC systems or in standalone units. Again, if we're going to be introducing these, we need to make sure that we're not preventing the system from working effectively. We can also supplement with portable HEPA filters. And there's also an opportunity maybe for filtration on people, for instance, people's desks or within their breathing zone. And that, I guess, is what we know is what masks do. They're air filters in your breathing zone. So what else does HEPA filtration offer us other than infection transmission control? Well, it allows us to extract inhalable and respirable aerosols from outdoors. It prevents those things coming in from traffic emissions as well. And it also allows us to take biological particles out of the air indoors. And one of the big upcoming threats that we're going to hear more and more about in the indoor air quality space is multi-antibiotic resistant bacteria, MAR. Most of the effort in the UK at the moment in the EPA is being put into biosurveillance of antibiotic resistance genes in the atmosphere and the environment. And this is something we're going to be facing, is systems that allow us to take away and reduce the risk of antibiotic resistance spread. A lot of talk about ultraviolet. So just a quick couple of slide on this. The graph here just shows you the wavelength of the different ultraviolet light bands, UVA, UVB and UVC. And we know that UVC has been very successful in deactivation of pathogens in aerosols. Traditionally, people are used to thinking about UV GI, germicidal, for germicidal disinfection. And UVGI sits at around about 254 nanometers, whereas more recently, there's been research coming out on the use of far ultraviolet light, which is slightly higher energy, with a wavelength of 222 nanometers. The difference between them is that far UV is being shown to be less damaging to skin and eyes, so that you can put them in an occupied space. The downside of them seems to be that there is some leakage into the wavelengths with far UV that may cause some production of ozone in a space. So a lot of research at the moment is going into making sure that if you use far UV, you're not producing the very high energy, releasing the very high energy wavelengths that lead to secondary pollutant formation. Recent studies looking at far UV is showing that you can kill 99.9% of a model coronavirus in 25 minutes. And in-room UV lamps have been in-room UV lamps have been shown to inactivate 98% of viruses in 5 minutes. But the thing that really sticks out here is that that organism has to be in contact with that light for the necessary residence time to allow it to destroy it. So we've got to think about how long and how quickly that air circulates past those lamps. So that's just to bring you up to speed with my understanding, which is fairly limited, but my understanding of where we are with ultraviolet light at the moment for preventing disease spread. There's other technologies we're seeing advertised, air plasma technologies, ionisation, even essential oils, some of which have got research that supports their use, some of which don't have research which supports their use. The University of Birmingham in the UK has just produced a paper on filters where they put antimicrobial products into the filters, and those filters not only remove things like viruses, but are actually destroying antibiotic resistance genes as well. There's even products like heating foam steel mesh, which is purported to destroy viruses. Given the fact that this has become such a key area of confusion for people, IBEC's actually going to be running a summit on supplemental technologies. We just heard that we've got the funding to be able to do this summit in the coming months. So we'll keep you posted, and I'm sure I'll work with AIRAH to help get that to you. So what is the future of our fresh air that we're trying to handle in our systems when we think about climate change? Well, increased temperature in the environment evaporates more moisture. Water vapour contributes to 50% of the actual greenhouse effect that allows us to live on Earth and keeps our environment warm enough to survive. But as temperatures warm, there's less cool air aloft, which means we don't get as much cloud formation, and you get increased airborne moisture in the air. And of course, that then increases global warming. And that then increases the demand on our supply, on our systems to remove that moisture. And in so doing, we're using more energy. So what we're doing is creating a positive feedback loop. So we need to work out other ways of being able to dry our air before it enters our building than just relying on something that's very energy intensive. So just a quick get into here now, but look at what technologies are available for monitoring our air quality. Plethora of real-time devices, apparently. Real-time, that should be. I'm sorry about that. Real-time devices are very good for looking at changes in air quality trends and patterns of contaminants across the space. There's instruments that we use for measuring volatile organic compounds, where we still don't have thresholds, which we'll talk about briefly. In terms of real-time detection of these pathogens and bioaerosols, at the moment, we don't have any of that technology. It's like searching for needles in haystacks because there's so much other noise that comes through with samples that actually doing something like giving you an instant detection of COVID in an air sample is very unlikely to be something on the table for a while. In terms of actually collecting samples and analysing them, when you have to collect a sample and analyse it, there's always a time delay in taking that sample and processing it. There's problems with consistency in how laboratories analyse methods, particularly around the mould arena. And there's issues actually keeping organisms alive when you sample them. So whilst we can tell you they're there, most of the sort of air sampling techniques are not great at telling you if they're alive. So by the time you've found out about them and you've taken your sample and gone away and said, oh, great, there was a pathogen in there, it's too late because everybody's been in there and they've already caught whatever you're trying to monitor. So therefore, we're still relying on proxy measurements. So carbon dioxide, we know, is really good for making sure we're controlling the level of exhaled air. Particle monitoring is really good for identifying hotspots where we might have an issue where we're generating particles that could be due to viruses. And humidity, just monitoring humidity generally, as we've seen, is very useful for making sure that we're not increasing the burden of contamination in our buildings by keeping it at a level certainly below around sort of 50 to 60%. The other thing which we're not doing at the moment, which we can do, is we can see if we can find an affected person. We can identify the person who could be the source of a transmissible disease, and we can do that through temperature. We can do it through taking a rapid antigen test. We look at ourselves and say, am I actually a source here? And the other thing that there's a lot of work being done and conducted in Australia with is wastewater testing for buildings. So that we can identify if a building is acting as a point source of contamination from infections in that building. And we're also wastewater testing to look for these antibiotic resistant things. So there's some of the methods available to us for monitoring. But overall, I guess what we want to start doing is coming up with a solution. And I think the solution to that is going to be management. And to come up with a transmission control and indoor air quality management plan, we've got to think about the risk hierarchy. You know, the further we are to the top of this triangle on the right, the more successful we will be in mitigating risks. The sources and risks for indoor air quality, and poor indoor air quality from airborne infection and from high energy use. We need to educate people. We need a process in place for educating people on what they need to think about to prevent air quality deteriorating and to reduce disease transmission. Disease transmission takes two people. It's not just the person that gets sick, it's the person that got the infection that's going to actually make other people sick. Learn about the risks and benefits of available technology, because obviously there's a lot out there and we need to know what's right for us, because we've got to pick the right trifecta if we're going to win the race and win the bet, because we need to think about when we use ventilation, where we use filtration, and where we need supplementary devices. We need to understand how airflows might change the movement of contaminants through the building. So there's tracer gas testing, which Brad Present is a leader in Australia, particle visualization. We're now starting to see DNA aerosol tracing come on board. It's a fascinating technology where we actually release an aerosol that's equivalent to the size of a respirable multi-phase aerosol into the environment and then track that through our building. And of course, there's computational fluid dynamics. CFD has always had a key part to play and continue to have a key part to play if we want to put together a comprehensive management plan for our building air quality. So when we're doing that, we need to think about people, because if we put the best management plan in place in the world, but unless we can encourage people to follow it, then it's just going to sit on the shelf like so many do. So this was introduced to me by Brett Cole at one of the IBEC webinars last week, where we looked at Maslow's hierarchy of needs. So what is it that people are looking for that they're going to respond to? Well, they obviously need things like food and places to go to the toilet and get a drink, and they need to meet their basic physiological needs. But after that, the next thing that people need is things that make them feel safe. They want to feel safe in their environment. So, you know, we need to think about what's going to make them safe. So following a risk assessment process and having people know that you've undertaken a risk assessment, can really help to provide confidence in the safety of that building. So programs like the Commit to Care program are fantastic for being able to take a lead in keeping your occupants safe, or even doing it yourself so you can assess your own level of safety in the building where you're working or where you're living. But it's our responsibility to continue to help people understand that masking still protects others and not just you. And we need to put in place systems to allow for people who protect others by wearing masks when they're not feeling well to be acknowledged as protecting the public. It's not just a question of COVID. We've had the flu. I mean, so many people have been sick with the flu. And we've had the cold. I mean, before we had the pandemic, the biggest concern scientists had was going to be an outbreak of a really serious strain of influenza. So we mustn't forget that this is not only about protecting people from COVID. We've learned these wonderful tricks that we can put in place. If people aren't feeling well when they go out, just popping on a mask not only protects them from feeling guilty because they've given it to the guy next to them who they didn't know had a granny at home who could get very sick, but it prevents them from spreading it when they're, for instance, travelling on public transport. So always communicate your actions to your occupants. Any changes that you make to your practices, I'd suggest that are communicated as frequently as possible to the people in your building. And remember, buildings also cause outdoor pollution. So we don't want to be releasing any more greenhouse gases than we have to. They can release manufacturing emissions, laboratories create emissions. We can release asbestos and lead-based paints and silica into the environment. We've seen several outbreaks of Legionella from cooling towers because their buildings are operating differently under partial occupancy. I mean, they can affect an area 6 kilometres beyond your building perimeter. And we saw an example of where not diluting the air in your building when it's got virus in it and venting it outside itself is dangerous because you're actually releasing virus into the outdoor environment. Change in land use, greenhouse gas from energy use, and emissions from wastewater treatment and solid waste is also there. So there we go. Sorry, I'm going to finish up here and say thank you.
I'll just read out the first question we do have for you here, Claire. And that one is part of the way of solving the energy usage of buildings can be helped by reducing the amount of oil heating and cooling by adopting better building standards for insulation, air tightness, and incorporating recovery?
Sorry, could you read the last bit again?
Yeah, the last bit is adopting better building standards for insulation, air tightness, and incorporating recovery.
Absolutely. I mean, I think that's going to be critical, and we know this from the sort of results we can see by things like passive house standards. So, yeah, I mean, I think it's absolutely critical that we do that for sure. And I think that's where we need to look and work as an industry.
Yeah, great. And the next one we have here as well, Claire, is how important do you believe the vaccinations are in keeping us safe?
Very. They remain keeping us safe from serious illness. And one of the most recent research on BA4 and BA5 is suggesting that it's very relevant in reducing long-term serious illness and also mortality rates in certainly the older population. The current vaccination is still providing some additional protection, but this is what has just come out of Israel. But it's less effective in younger people at reducing that the serious illness, but nonetheless it's still having an effect. And there are new vaccines coming into place. Certainly around October, we're expecting to see vaccinations coming out for the new variants. The problem that we've got is until we stop transmission and we stop the rate at which this is spreading through our communities, that virus is just going to continue to be given opportunities to mutate. And that's the issue. We've gone down a ventilation avenue, which is absolutely correct. But we have to think about our ventilation and our source control and trying to reduce transmissibility, because otherwise it's just going to constantly be a race of vaccinations trying to keep up with the new variants, because once you have a pandemic virus, it doesn't disappear. It's going to be with us potentially forever, or certainly for a very, very long time, until we come up with a vaccine which is more generic, which again people are researching and trying to come up with. But at the moment, getting vaccinated is still the best advice, and it's a key control mechanism in reducing transmission.
Thanks, Claire. And the next question we have here is, do modern photocopiers and MFD still produce emissions that need to be exhausted?
Almost, yeah. I mean, we're very concerned about nanoparticles, which are released particularly from printers, and again from MDF. And I would say that again, if there are point source and it's in a single place, then exhaust is the right way to go forward. Trying to dilute a contaminant that's come from a point source by ventilation is like trying to give an elephant an anaesthetic to cut a toenail. We need to think about point sources and how we extract air from them. So yes, I would say so.
Yeah, great. And the next one we've got here as well is David's asking, can you talk to some new or older methods for air washing? He's seen a very old oil mesh filter one time ago and has been intrigued by it. So are you able to chat a bit about that?
I would love to, but unfortunately it's completely out my area of knowledge. I think that would be a great question for Patrick when we have our next session. And if he would like to drop us a line, I'm sure we would do our best to come up with something to help him.
Yeah, great. Another one we've got here as well is, are you seeing much retrofitting of existing buildings to improve indoor air quality in the UK?
Again, my knowledge of the UK is limited. I have the members that I'm speaking to at IBEC. I could certainly find out a lot more accurate information for you than I will probably give you by giving you a sort of seat of the pants response. Certainly, I know that there is a lot of work going on over there for reducing particle levels. But in terms of retrofitting, there was certainly some very interesting retrofitting done in the UK some years ago, but it was around energy efficiency. And this is a really good example of why retrofitting needs to be handled so carefully. The southwest of England had a very large number of social housing areas, and they went and made these buildings much more airtight to help reduce the energy costs of those buildings. And the asthma rates in those buildings just shot up because all of the indoor contaminants were now just contained, and the buildings weren't designed to handle, just even things like the gas fires that they had running. So, it's a question of thinking broadly about what are the impacts of making that decision, and I'm sure the same thing is true there.
Thanks, Claire. And another one we've got here as well is, Peter is asking, did we correctly understand that some suggested air cleaning technologies could introduce problems such as contaminant byproducts that may deteriorate health, etc.?
Yeah, absolutely. So that's what my slide on ultraviolet was all about. So what we know is that UVC is a very large spectrum of wavelengths of light. And the very high energy end of UVC has the ability to create ozone from oxygen. And that ozone then becomes a very powerful oxidizing agent, and it can interact with other gases in the indoor environment and create worse compounds than you started with. And ozone itself is not a safe gas to be inhaling. It protects us from incoming radiation from the sun, but we really don't want it in our breathing area. And so what we found with the standard germicidal UV light, that's about 240 nanometers, I believe. They had a 0.3 at the end of it. With that particular wavelength of light, that doesn't tend to produce a lot of byproducts in terms of secondary pollutants, but it has been shown to cause problems with sort of skin and eyes. So it's great to put it in your HVAC system or someone like that where people aren't exposed to it, but you can't put it in the occupied space. With the far UV, which sat around 222 nanometers, that is not causing, or doesn't seem to be causing, the same health effects in terms of skin and eyes but there is some leakage in, because it is a higher energy wavelength. When you've got the light bulb, obviously you've got the source inside the glass. Some of the wavelengths that are coming through are still in that area where they could cause those reactions to take place. So there's work going on with the manufacturers and people developing far ultraviolet products at making sure that those lower wavelength and higher energy radiation sources don't come through.
Yeah, thanks, Claire. Look, another one here is have you got any advice on how we can manage dirty outside air coming from the side of the road?
I guess that's where our fresh air intakes come in with mechanical systems. In terms of if you're in a naturally ventilated environment, then obviously it's more difficult, and by the time it comes into the building, it's no longer a point source, it's now mixed in with all your air, which is probably fairly freely mixed with it in there. So then you're looking at using things like portable filtration systems to manage that.
Yeah, great. And just another one here, I think, before we start wrapping up the session, Claire, is just a question around the effectiveness of masks and social distancing and hand washing. Do you believe these are still important?
Very important, because one of my later slides, which unfortunately I'm out of time, is that COVID and flu are not the only viruses we live with. There are still stomach viruses, noroviruses, adenoviruses. We still have a lot of viruses in our environment, including monkeypox, which we know are spreading through person-to-person contact. So we still need to be very vigilant about disinfection and hand washing, because COVID isn't the only pathogen that we've got, even though it's the only one on a lot of people's minds.
Yeah, great. I think we will wrap the session up there. I know we've gone a bit over time, but if anyone does have any more questions for Claire, of course, obviously feel free to reach out to Claire or myself. But that does bring us to the end of today's session, everyone. So I just want to start off by thanking everyone who registered and attended today's webinar, but of course a big thanks to Claire for conducting today's presentation as well. The recording of today's webinar will be made available within the next couple of weeks. And as always, I'll send through a quick email to let everyone know when that's available for viewing. To view or register for AIRAH's other upcoming Streamline and or Technology Talk sessions, please visit the AIRAH website. There's also a list of past recordings up on our library page for you to check out as well. And as Claire touched on just before, we'll be looking to conduct essentially like a part 2 session of today's presentation that will effectively dive into some more technical details. But we'd love to hear your thoughts on what you would like the presenters to cover off in the next session, so that way we can get the presentation tailored to what you guys would like to hear more of as well. So if you could feel free to drop us a line or fill out the feedback survey when I do send that out, that would be really helpful to us going forward. So thank you all once again. Thank you, Claire, for a very informative session. And until next time, take care, everyone.